To hopefully clarify some of the symbols we use, let's do a concrete example with numbers. 10 centimeter inner wheel, total moment of inertia 0.006 kilogram meters squared, and a 0.3 kilogram mass descending through the displacement delta y. So, magnitude of delta y is just 40 centimeters. Of course, it's in the downward direction. If we isolate the wheel, and we got the mass here, that means we're going to have a downward force that's approximately 3 newtons. And it'll be negative 3 newtons times J. We have our R vector here, and let's this time use the R vector from here to the actual point of application. So right here would be the more appropriate R vector, and this vector here would be the L vector, the lever arm vector. So we have a lever arm, 10 centimeters in this direction, negative a 3 Newton force in the downward J direction. The L is 10 centimeters times the I direction. So what is the torque? Well, torque is this force crossed with the L vector. The L vector crossed with the force. I guess I can put that over here. And that's the same thing we would get if we crossed R with F. We can't really cross R with F because we don't know just what this vertical position is here. We don't know where the mass was when it started, so we don't know where the mass is at this point. We don't even know when this is. So the tau is the L cross F, and that's going to be 10 centimeters times negative 3 newtons, which is negative 30 Newton centimeters. And then that's I cross J being positive K. I cross J, you get positive K. So we get the torque being negative 30 Newton centimeters times the K vector. And of course that's going to be negative 0.3 Newton. Well, I don't want to call it Newton meters because it looks too much like work. I'll use meter newtons times the K vector. So there's your torque vector. Now the magnitude of delta theta is arc distance divided by radius, and that's going to be 40 centimeters divided by 10 centimeters, which equals 4 radians. So we got our magnitude of delta theta. If you want the vector delta theta, delta theta is 4 radians around this way. Right-hand rule says that's into the board. So if we want to do delta theta as a vector, which is not absolutely necessary here, but if we want to do delta theta as a vector, then it's negative 4 radians times K. Now what's our work? The work done on the system by this gravitational force, and of course that's going to be equal and opposite to potential energy change. The work done on the system is tau dot delta theta. And I'm using the vectors right now. Okay, so tau is negative 3 meter newtons times k. Delta theta is negative 4 radians times k. And that equals 12 meter newtons. A meter times a radian is still a meter, for reasons we've talked about before. Meter of radius here times the radians gives us meters of arc, and that's where the work is done. We get 12 meter newtons, but now the meter is a meter of arc, not a meter of radius, so the meter newton's no longer torque, it's work. So we have total work done is 12 joules. Now what else can we determine? And you might want to pause and think, what else can we determine about this motion? Okay, well, we've got I. What can we do with I and the work? Again, think it through before I explain it. Okay, well, this is the work done by the net force on the system. If we assume no friction, no air resistance, and so forth. So if this is the work done by the on the system, then change in kinetic energy is the work done on by the net force, which is 12 joules. And the change in kinetic energy, if we assume the system started from rest, we quickly conclude that the final kinetic energy is 12 joules. Okay, what can we do with that? You should think. Okay, gave you a chance to think. Final kinetic energy, of course, is 1/2 I times omega F squared. That's our 12 joules. I is 0.006 kilogram meters squared, so that omega F is the square root of 2 times 12 joules divided by the moment of inertia, which is 0.006 kilogram meters squared. Okay, now let's say that's 24. And hang on a minute. I'm off a little bit. This is going to come out pretty big. Hopefully you caught this before I did, but this is 0.3 meter newtons. I copied it wrong and didn't have my brain working at the time. Having a little trouble with that tonight, but okay. That's going to be 1.2 Newton meters, 1.2 joules. Okay, and, you know, it's 3 newtons through about 1/3 of a meter, so it's going to be around a joule. Something's still wrong. I'm not going to worry about it here in a minute. So we're getting 1.2 joules. Hopefully if there's something wrong, you see what it is. Right now I don't. So that should be the 1.2 joules. And now we're going to get a more reasonable result. That's going to be 2.4 joules. You've got to divide that by 0.006 kilogram meters squared. And I believe that's going to give you the square root of 400. The units, joules over kilograms, that's kilogram meters squared per second squared over kilogram meters squared. You get a reciprocal second squared. which gives you a second to the negative 1, gives you 20 seconds to the negative 1, which is 20 radians per second. I'll explain that in a minute. I'm going to pause the video for a minute here and see what's not computing. Okay, that was rather easy to see. Tau was negative 30 Newton centimeters here, and now I've got an arc distance of 40 centimeters. I'm sorry, delta y was 40 centimeters. Okay, torque, actually, I was looking at the 30 here, thinking it was a 40 there. So I'm going to hold myself harmless here. I thought I made an error, but I didn't. Okay, so that all works out. Now, this 20 reciprocal seconds. Remember that over here when we divided the meter squared by the meter squared, at least one of these meters was a meter of radius. Actually, they're both meters of radius. And this, I'm sorry, in calculating the work, those are meters of arc. And in calculating the moment of inertia, we're using meters of radius. So we have meters of arc divided by meters of radius, each of which gives us a radian. So we're going to have radians squared out of this calculation. So we could have put the radian squared here and here, but in any case, well, we put the radian squared under the square root here. It would come out as a radian. So instead of 20 reciprocal seconds, we got 20 radians per second. Again, you don't have to be conversant with all of that reasoning. It's good if you can, but you can get by if you just kind of regard radian as a phantom unit that comes in and out when you're multiplying, dividing meters.